I've been deep inside of the process of updating the Beekeeper for a run. That includes updating the sheath with some features. I've had a couple hiccups along the way, and I thought it would be fun to take you guys along, see a little bit of the inside baseball, and have a little bit longer, more informal conversation on like deeper into the details of what makes sheaths work and these problems that I've come across. Part of the reason that I wanted to talk about this is because I feel like it's a really good example of incremental improvement and how you can take these small steps and you have to accept the failures along the way in order to improve a process and get to a place you might not have known that you could go. That sounds super motivationally and stuff, but anyways, I think that's the bigger picture here, but let's get into the details of sheaths. This is what we started with. So this is the last full-size Beekeeper sheath, and I'm actually really happy with this sheath. There was nothing wrong with it in particular, but I did want to add this right here, which is an adjustable divot. So all the new sheaths that I've been doing, as I do another model, I'm updating a sheath as I go along. And that's one of the things that I originally did. I think the gut plug was the first one that I ever tested that out on. See the adjustable divot right there. And I liked it a lot. And so I've been slowly, as I've been doing more models, I've been implementing that into the new molds, basically. And the reason that I like the adjustable divot so much is you have your knife is going to last a super long time. If you take care of it, your lifetime, maybe plus some. I want the sheath to last as long as the blade itself. So having an adjustable divot there means that, even if you sharpen this blade a whole lot, you're not going to get to a place where the blade rattles in the sheath, because you can just tighten that divot and adjust it for wherever you're at in terms of blade wear. Or sheaths break in too, so it's like it doesn't rattle now, but maybe if you're using it in rough environments, like some materials getting lost, etc., I want that sheath to be able to last the lifetime of the blade. So that's really the whole goal with making this small little adjustment. But along the way, so this was the goal, is like adding that one little feature to an already good sheath, which is this one right here. But along the way, I found a couple things. I destroyed these sheaths so that I could learn a little bit more. And I actually found a better way to do things, period. So that's what I wanted to talk about a little bit today. So, real quick. This is a Beekeeper in 1/8" stock. So the regular Beekeeper is 3/16" stock. It's a thicker one here. We're also adding, we've done them before. I've done them before. But it's going to be a more permanent fixture in the lineup now, is the thinner Beekeeper. It's great. This one is super hefty. Like it's a tank of a knife. For batoning, and if you want to super rely on your tool, that's a great way to go. If you wanted a slicier, more lightweight option, this 1/8" Beekeeper is a really good option. I think this is going to be really well suited for general camping, hunting, general outdoor stuff. Obviously, it's still 1/8" stock, so it's not like it's a crazy thin knife, and you still have that geometry where you'd maintain the full thickness to the end. Anyways. I'm not talking about the Beekeepers here. I'm talking about the sheaths. So back on track. But that's why we're doing two. So that's why you see we started with this one original Beekeeper sheath. And I always mark on the sheath. Since I have so many of these molds floating around, I always mark on what their status. So these are scrap, so they just get an X. But, the old or obsolete ones, I mark old or obsolete. And I keep them because it's might as well. There's probably another, I don't know if there's another Beekeeper one floating around. I don't know if this is the original. This probably is not. But anyways, so, I made these first molds. by the way, real quick, side note to the side note to the side note. I made a whole process on how I do my entire sheath process. If you want to look at that video, I'll have it linked down below, but we're not going to get into the whole process here. But we do make our own molds. We mill them out of HDPE, and that, you know, it's a big learning curve to like start doing that. But now that we have that skill set, it's really nice. So when we want to make a, you know, a minor change, we can do that. Typically not with this many hiccups along the way, but it's really nice to have that ability in-house. So anyways, we added our adjustable divot to the model. So the 1/8 inch, so we can get the light right so you can actually see it. So there's our adjustable divot. These are really hard to film. There you go, right there. So, and on this 1/8 inch one, since we had to adjust the heights of everything, this divot height was immediately off. So I knew I had to make a new 1/8 inch mold right off the bat. That's why, here, I can show you. So this sheath here, it's actually too tight. So had to adjust that. And then for the 3/16 one, you know, we knew we had a good sheath to begin with. I made a couple little adjustments over here, but really we just ran the same divot height and then added this little piece right here, and that worked well. The issue with both of these sheaths was right here, basically at the end of the adjustable retention spot, as as the blade goes into the main cavity, there's a little like step down, and the blade would get caught on that little lip, and it would basically cut away a portion of it. You're probably not gonna be able to see if I show you inside here, but basically, like, what would happen is when you first put your knife in the sheath, it would grab and you could push it through, and you would slice a little bit of kydex away. After you did that a few times, you know, and sliced not a whole lot away, but, you know, a significant amount where you're noticing it each time. After you've removed that little bit, the sheath worked great. It went in without catching every time. If you'll be able to see that in there. I'll try and get a shot later of this, but if I have that shot, I'll insert it right here. Anyways, that wasn't ideal. You know, you wanted the sheath, you don't want the knife to go immediately in, click. You know, so a sheath does a couple jobs. I wrote this down, so because I was gonna forget about this. It holds the knife, it has to release the knife, it has to be small, relatively small. It should be adjustable, it should be mountable and versatile, and it should not harm the blade. So that's kind of simple what a sheath does, but actually getting it to perform all those things well and be usable is a little bit trickier. So anyways, so I knew we needed to adjust the divot on this 1/8 inch sheath, so I made a new on the mold. So I made a new mold, but I also did something to address the catching of the blade in this portion right here. Instead of like following the exact profile of the knife at this base, I made it a little bit wider. So basically, like, because what was happening is the blade and the spine were both touching, and it was wedging itself in there, and then it was, you know, sliding to the center. You know, so if you inserted your blade at any sort of angle, it would catch on that outside material, cut it away as it straightened on the way in. So if you inserted your blade perfectly straight into the sheath, you know, you wouldn't have a problem. But that's not realistic to expect of people. And part of the reason that we are experiencing this issue in the first place is how we design our sheath to begin with. And it kind of goes to the not harm the blade part of that. So on these sheaths, this part, this where the blade is in there, the reason that we have to put a divot is because this is so wide. There's so much of a gap on either side of the blade that you have to have this little spot to touch the blade so it doesn't rattle. But we try and minimize that spot so you're not like wearing your blade, you know, because we could just put this where your blade has friction the whole way in and it's getting scratched every time you insert and remove it. Like this blade has been inserted and tested with those sheaths a bunch of times, and you can see that little spot right there. See that little shiny spot? That's the little, it hasn't even removed the heat treat finish from this. But you see it's gotten a little bit polished right there. So that's the amount of sheath that touches the blade. So it's pretty minimal, but otherwise you would have, you know, if you had it perfectly fit to this blade, then you would have it scraping along the whole way. And yeah, so that's why we do that. I recently got this whiteboard at the thrift store for $2, so I thought I'd put it to good use. What you're seeing here is a rough estimation of the sheath in black, the blade in purple, and then the divot in red or pink. And so this is why I cut the tips off these sheaths. This is where the divot actually is. That's about the midpoint of the divot, roughly. And so you can see if it'll actually focus on that. You can see kind of that structure right there. So, you know, we have our top where our spine is hitting, and then it, you know, our divot is touching right there. This one actually, it's not touching. It's a little bit loose. This is the one that I have marked bad, and then I labeled it that the gap is too small. So this is when I was playing with this mold. So I actually, this was too high originally, so I used a Dremel to grind a little bit away, and then I ground too much. So I had a little blue tape to try and dial in the exact right height. From there, once I dial in it with blue tape, you know, I have the good sheath right here. Okay, there it is, no rattle. I know that one's good. I can just measure this distance here and take that into CAD and make my really good model that doesn't have tape all over it. The reason that we have this gap right here in the first place, you know, all around, even here up at the spine, there's a gap on either side of the blade. Big gap on either side of the blade, going all the way down. That's on purpose. That's how we build these sheaths, and that's what you could see in the cutaway section of the real sheath. That's so that there's no Kydex touching the blade, and I design it with a little bit extra gap so that if you are in like a dirty environment, you have dirt or sand, and that finds a way in your sheath. You know, if there were a little piece of sand and this gap were much shorter, that could wedge itself and just scrape your blade the entire way down the sheath. So we start with a really big gap here, and that's why we were originally getting the cutting of the sheath, is because since it's such a big gap on either side, the sheath can move left and right. So there's a downside to both. You know, you want a big gap so the blade doesn't touch the edge of the sheath or the walls of the sheath, but that also gives it degrees of freedom to move. And that's where we were having the issue with it cutting into the wall. So how can we get this and the benefits of this without compromising, you know, functionality? So that's where on the next mold, we made this portion right here at the base of the blade wider so that there was no possibility of the spine and the blade wedging, because this dimension here was so much wider. Let me draw that. Okay, here's maybe a better representation of what's going on. So here's the blade in black, and here's the little bit of extra width that we gave to the sheath. So that's right here. At the base of the sheath, it's a little bit wider and only meets the actual profile of the blade right here when you start to get to this belly towards the tip. So during this whole parallel section, there's no place where the spine and the blade can wedge together. Also, the further you get down the blade, the further your knife goes into the sheath, the less likely it's going to turn either way, basically. So once you get down here, there's really no likelihood, like there's not enough degrees of freedom at the handle to allow it to hit any of that. That's another reason why we have the divot further down the blade and why it's so round like this. Because you can imagine if we were just to, you know, do a block and our blade is coming in like this, you know, here's our edge. You could cut into that as your blade is getting pushed down the sheath this direction. You could hit that wall and it could just stop right on the divot instead of going all the way to the tip. So instead we round that so that the angle of the sharpened edge is steeper than the angle of the divot. So even if it hits that divot, it's just going to bounce right off and not grab in and cut. So that's a bit of like the internal geometry, and that was the solution that we found to solve this problem, which was actually super nice because now we have, you know, this portion right here where the sheath is grabbing on the scale, retains it forward and back and left and right. So this portion right here really locks it in that position. And then at the tip, you know, you have this taper here, and that really locks the blade in along with the divot. So, you know, if you have your divot lined up right, this blade can't move farther down. And it definitely can't move this way or that way because of this. And so that fully constrains your blade in the sheath, and you get no rattle. That's what we were looking for. And so this was a success because we're not having this portion get cut by the blade anytime. So you can just, you know, haphazardly throw that sheath on and it finds its way home every time. So that was a pretty big win. The cutting issue was a bigger deal on the 1/8 inch blade than it was on the 3/16 blade. It was like, I mean, maybe you inserted the blade twice and it had removed enough kydex that it wasn't an issue from then on out. But we went ahead and made a new mold for the 3/16 as well, kind of following this principle, because why not? You know, so now we have two sheaths that are, you know, ready to last the lifetime of the blade and don't wear the blade in a minimal way. And it wears the sheath in a minimal way because it's not cutting into the sheath. That's a pretty big win in my book. I do want to talk about one other thing. So the original sheath, if you can find it in the light right here. So it had this pretty big chamfer all the way down. And what I actually found out is this divot didn't need to be as precise because the blade right here at the tip was actually wedging itself into the kydex at the end over here, like on this portion of the blade. So not at the tip, but at the spine behind the tip, basically. It was actually wedging into that portion right there, which wasn't a big deal. It wasn't causing any problems, except for when we took that to the 1/8 inch blade, where it wedged much more aggressively. And basically this thing was happening where if you stuck the blade in like perfectly along that front line, it would stick in higher, and then you could basically like wedge it down and then it would rattle a little bit. So you could kind of get this like false sense of like, oh, there's no rattle, because it was actually wedged in the top right there. Like the knife was actually wedged in the kydex. That wasn't great because whenever the knife is wedged in the kydex, there's some level of friction to remove it from that wedge. And if you were to like tip down just a little bit, you would avoid this top spine section of the sheath and it wouldn't wedge in. And then you would have a different sounding click. It would be like more of a thud when it wedged into the kydex, and more of a pop like you're hearing on this sheath when it didn't. So you're getting inconsistent audible and feedback, inconsistent feedback and an inconsistent draw. So we changed that by doing a smaller chamfer and really dialing in the divot. So everything, like as far as like preventing rattle, relies on these two spots right here. And that makes it more consistent too, and more predictable, which is what you want a sheath to be. So it's these little small things that are not deal breakers, but if you can fix them, fix them. Okay, so this is the point where I would like to talk about this sort of like incremental improvement over time. Because if you are picky and you consistently do these incremental changes, it pays off. It doesn't seem like a lot in the long, like that. I spent a lot of time, like making molds, doing CAD, cutting up sheaths to fix this one little issue. And it's like, dude, it seems like you wasted a week, doing this. But if you zoom out, it's those little, hopefully everything doesn't take as long as that took. Hopefully now that I learned all this stuff, the next time I run into this issue on another blade, I can solve it that much faster because I've already come across this and I already have that knowledge, in my skill stack, whatever. A good example, internal temp too high. Fuck me. My camera just turned off because it says it was too hot. It's only like 95 in here right now. Come on, camera. Come on, Sony. It's Texas. Get used to it. Okay. So what I was saying before the camera so rudely cut off on me was these small little incremental improvements take a lot of time, at first, and they feel really insignificant in the short term. And I'm gonna kind of show you, so this is the original gut plug. So this sheath was hand formed. These bevels were freehand ground, and the scales underneath that goon tape were hand ground. A very, labor intensive process. Slowly over time, this is the next iteration. I didn't do these back to back. We basically run these once a year. So this is like all my cumulative improvements over a year get applied to the model that I'm running at the time. So it's kind of interesting. You kind of see this is where I'm at each year. So this is the next year. We have a vacuum formed sheath with CNC'd scales, and I actually used a little jig to grind these bevels, so I wasn't just totally freehand grinding them. The vacuum forming was a big deal, and that really allowed us to do a lot more of these. That's kind of the cool thing is, I spent the same amount of effort, but we were able to do so many more because of these improvements, and the quality is actually a lot better and a lot more consistent. And then you move to the third iteration of that same knife, and we have again improved the sheath. The scales are still CNC ground, even though we're using a little bit different hardware. Another improvement. So on the old hardware, you have to drill a counter bore. So there's 2 bolts and a standoff on each of these holes, and you have to counter bore the inside of the scales to fit that standoff. And that was a manual process, and it is an area where you risk messing up the scales completely. So anyways, with these, there's just 2 pieces. There's, a female and a male portion and just 1 through hole. So basically I pop these scales off the CNC router, bolt them onto the knife, and then I'm ready to finish with the profile grinding. These bevels were done on the bevel machine. I'm not going to talk a lot about that. That's like a behind the scenes project right now. I've been told by a lot of people to shut my mouth, stop talking about that machine, and just work on it in the background. So that's what I'm doing. But these were ground using that machine, and the sheath was improved on, still vacuum formed, but we have a way more adjustment on these actually, because I found, I was listening to user feedback and hearing that people wanted to run these like on their belt. This is designed to run on your belt, like outside of it. So you needed the retention to be pretty solid for that setup, but people also wanted to put a DCC clip on these and run them in their pocket, where you would want a lot lighter of a retention. So adding this retention, so you have two adjustments right here, and then a second hole right here if you really wanted to crank down. The closer you get to your actual retention point on the scales, the tighter you can make the retention. So having those 3 adjustments for it are really infinite. I mean, not infinite, but you have a very wide range of adjustment, ranging from really loose to super tight. And that covers everything you need. And then we have this is the first time that we ever did the adjustable divot, and that was a huge success on this and really made this sheath reliable. If there's variations in the bevels, if there's variations in the scales, this sheath ate up all those variations. And it's like, okay, cool. So we made some improvements from the last one, but then you go and look at like the original knife. You're like, oh wow, like, in 3 years, this is the improvements that we've made. And the nice thing about all these improvements is these are process improvements. So it's not just like I personally got better at making knives. It's like the process that I use to make these knives got way, way, way better. And it's approaching scalable. That's the whole goal with this. But, to go from here to here, you first have to do this. And in order to go from here to here, you have to spend the time in the weeds messing with sheaths like this, hand grinding your vacuum molds, putting blue tape on them, refining them, measuring, redoing. So this is kind of like the dirty, unsexy grunt work that leads to, when you step back a few years, leads to significant improvements that make your life better, make the customer's product better. It's a win all the way around. So that's kind of what I wanted to say with this video is like, if you have a process improvement in mind, if you're interested in improving your processes, period, it's worth it, because now that I've put all the effort into this vacuum mold for this sheath, it's done. If that mold wears out, I'll just mill another one. They don't really wear out, but I'll probably have another improvement before it wears out. But you get my point. This is not a perfect sheath, but this is a sheath I'm really proud of. It just works. So I'm not trying to toot my own horn. My point is, this stuff, sitting here cutting up what was actually a usable, functional sheath, seems counterproductive, seems like wastefulness. But if you zoom out far enough, this is actually super productive. And this, little cost in materials can over time yield some pretty significant results and improvements if you keep doing that, And I think a part of this is if you are trying to do this and if you see the benefits in doing this, you have to be willing to fail. You have to be willing to just try something and waste the money, like this HDPE. These molds were basically immediately scrapped. These never went into production. These three molds, were immediately scrapped. HDPE is not cheap. The time on the machine, the wear on the machine, it all costs something. But you kind of have to put that aside in your mind and just try it, because if you don't try it, you're guaranteed to not improve. Whatever shots you don't take, blah 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 blah. But anyways, if you'd like to see, let me grab a good mold. if you'd like to see the process, the entire sheath making process that we use here, everybody does it a little bit different. So I found it's really helpful to like look at how, you know, different people do it and take what's useful to you and throw away what's not. So if you want to know how I do the full sheath process, I'll have a link in the video. So thanks for watching. I hope you got some value from this. One more thing quickly before I forget. So part of the reason that I'm proud of the way that I do sheaths, and I really enjoy the way that I do sheaths, is because I can do all this work on the mold, and all I have to do after that is print off one little trim mold for the trim router, and you know, put some wooden dowels in here to hold the sheath once it has holes in it. And that's the only other thing that needs to happen, that needs to change for that new mold to hit production on the sheath. So that's kind of cool too, is like, you know, there's not like these complicated fixtures or expensive fixtures that I have to now change because I've updated the sheath. There's very little friction in the way that we do sheaths to updating the sheath, which is nice, because, you know, any little bit of friction is a disincentive to make those little improvements. Thanks.